Section 1.2, Kinematics in One Dimension. In this video, we want to talk about kinematics in one dimension and apply some of the math we learned into some new scenarios. Before beginning, we have a couple of preliminaries to cover. First, we will start with some assumptions for classical mechanics. The first of these assumptions is that space is three-dimensional. Thus, we can assign three different axes: an x-axis, a y-axis, and a z-axis. Now, before beginning with 3 dimensions and 2 dimensions, we need to get our footing with 1 dimensions. We'll also assume that our space is Euclidean. Now, what this implies is that we can use the Pythagorean Theorem in order to measure distance. This is, again, important in 2 dimensions or higher. Thus, if we have a triangle, and I know this side, and I know this side, well, I can find this side by taking x squared plus y squared to the 1/2 power. The second assumption that we want to make is about time. In classical mechanics, we want to assume that time is something that is separable from space, such that if we have one clock from the point of view of one observer, that will be in sync with the clock at another observer. So in essence, time will not change based on location. This is something that we take for granted in classical mechanics, but of course in relativistic mechanics, that is something that we need to lose because we are dealing with a 4D space-time as opposed to a 3-dimensional space and time being separate as we do in classical mechanics. A couple more assumptions that we want to make is that we will use simple objects. What do I mean by simple? Well, simple essentially means that all objects are points. This is something that will not be the case in Mechanics 2, where you deal with rotation, but currently we will deal with all particles as being points. In addition, we'll also consider systems from a point of view that is far away from the observer. Finally, for now, we will be looking at kinematics, at least with projectile motion, as an assumption that the Earth is going to be flat. So we will not be dealing with curved Earths at this point. We will be dealing with flat planes. That's going to make calculations a lot easier for now. Now, in order to set up one-dimensional kinematics, we are going to draw a little picture and look at the invariance of certain quantities. So we are going to have a line. So here's our line. And this is our one dimension. So you could call this the x dimension. So on this line, we're going to have a point P. So we'll call this point P here. This is point P. And we are going to have an observer. This observer is going to be O1. Okay. Now we are going to say that P is a distance x from O, or distance x sub 1 from O. So you define this value. This value is going to be x sub 1. This is the distance between O and P. So once we have a function of how P moves through time, then we know all that we need to know. We know how far it's going to be away from O at any given time. So this implies that x is going to be a coordinate. Now, once we have this x of t, that's all we need to know. Now let's add another observer. We'll call this O sub 2. This is O sub 2. And from O sub 2, we are going to be a distance x sub 2 from P. So it will be a distance x sub 2 away from P. So both our observers are going to disagree about how far P is away from them because, well, they're at different values to start with, so of course they're going to disagree about where P is. However, as P moves through time, they are going to agree about how far away P is. So if I have another point, if P maybe moves through time to P prime, well, then the little amount that we're adding to get to P prime to each of these is going to be the same. It's going to be a same delta x. So delta x is going to be the same for both. So both observers are going to agree on delta x, and they're also going to agree on the time. So because we said that the clocks are the same everywhere, observer 2 and observer 1 are going to agree about how long it takes P to go to P prime. So we can agree on the displacement and the time interval. All right, so now I would like to look at some important quantities. So one of these important quantities is the average, or is the displacement. So definition. We have the average displacement, which we call delta x. Now delta x is equal to x at its the final position minus the initial position. And this is going to be units-wise in meters, or in the units of length. And we put brackets around to indicate units. So this could be meters, maybe. Okay, well, we also have a time interval. So delta t is going to be the final time minus the initial time. And in units, this is going to be in units of time. And in our case, we will usually like to use seconds. Okay, now with both of these values, we can obtain some more values. So let's say that I want to find how fast something is going. So if I want to find how fast something is going, I'm going to want to find the average velocity. So the average velocity is going to be, however, to denote average velocity, I use v bar. And this is equal to how much the position changes divided by how much the time changes. And this is in units. And I'm going to drop the time and length units because we know what meters and seconds are. This is going to be in units of meters per second. Finally, we can define the average speed as being equal to the absolute value of the average velocity. And this, again, is in meters per second. Okay, now what we can do is we can change this average velocity into some sort of instantaneous velocity. So as you see, we have a delta x over delta t, and this looks very similar to what we had in the last video, where we had delta y over delta x, and of course that became a derivative in the limiting case. So what we're going to do is we are going to take the velocity and turn that into the limiting case. So if I put in another definition. So if I want to find the velocity at any time, the instantaneous velocity, well, that is equal to the limit as delta t goes to 0 of delta x over delta t, which is equal to x dot. So this is the first derivative of position. So if I have my position function, x of t, then I can differentiate it to get x dot of t, which is equal to v of t. Wonderful. Finally, we want to introduce another quantity called the acceleration. So another definition. The acceleration, the average acceleration, is equal to the change in velocity over the change in time. And this is in meters per second squared. We can take a similar limiting process to get the instantaneous acceleration, such that the acceleration at any time is equal to the limit as delta t goes to 0 of delta v over delta t, which is equal to v dot, which is also equal to x double dot. So now we have our full definition. So if I have x of t, I can go to v of t by differentiating, and I want to differentiate again, and I get a of t. So differentiating will bring us from a position function to a velocity function to an acceleration function. All right. Now, one of the next things I want to do is discuss the integration of the equations of motion. Now, the integration of the equations of motion is an application of the last thing we talked about in the last video, which was the separation of variables to solve differential equations. So we will be using that to derive the equations of motion. So if we want to get from acceleration to the position, we will need to integrate because we needed to differentiate to get to the other way around. But acceleration is going to be more fundamental than position. So we are going to start from acceleration. So let's say I have a of t. We know that this equals the derivative of velocity with respect to time. Okay, so now I have something that looks like a separable differential equation. So what this allows us to do is this allows us to integrate this. So we are going to move all factors with t onto the left side and all factors with v on the right side. So we get a of t dt equals dv. So I'm going to move this around a little bit, and we're going to do some integrals. So we're going to get the integral. We're going to go from some v naught to v of dv, and that's going to be equal to the integral between t naught and t of a dt. Okay, so from here we can derive some equations, but not all. So we can find two equations. Just from this method, we can determine that the velocity, or well, we'll continue with this here first, and then we will put that down there. We will perform the integral on the left-hand side, and that's just going to be a very simple application of the fundamental theorem of calculus, which says that v minus v naught is equal to the integral between t naught and t of a dt. Okay, so what we're going to do is we're going to rearrange this to find a function of v, or a function of t that models our velocity. So we get v of t equals v naught plus the integral between t naught and t of a of t dt. And we can do the same with position. I will not go through the same derivation that we have because it's the same. But it's going to be x naught plus the integral between t naught and t of v of t dt. So those are two fundamental equations. However, now we are going to be able to solve this more fundamentally from position. So we found up here, we found this equation here, but now let's take it a little bit farther to find position. So we can solve this equation. So we have x of t equals x naught plus the integral between t naught and t of v naught plus v naught plus the integral of between t naught and t of a of t dt. So if you were able to find the acceleration function, you will be able to perform this integral. But we don't know what the acceleration function is, which makes things a little bit tricky. Now what we can do is we can distribute and use the linearity of the integral to further simplify this equation. So we get x naught plus the integral between t naught and t of v naught dt. And then this will be plus the integral t naught and t, and we have another integral between t naught and t of a of t dt dt. So we have two dt's, so we're integrating twice. That is not a double integral, but rather it's an integral that you then take the integral of. So we're integrating over t twice. Now what you may have noticed is that this first integral we are able to do. So we get x naught plus v naught times t minus t naught, but we still have this other integral between t naught and t, again between t naught and t, of a of t dt dt. Okay, so that is the case where we have an acceleration function, but we also have a case where we may have a constant acceleration problem. And that's really what we're going to be dealing with. We can integrate these acceleration functions if we need to, but it's really nice in kinematics when we have constant acceleration. So again, we're going to go through this similar process, but we are going to do it once we have a better idea of what we're looking for with the constant acceleration, and that will allow us to actually derive some very important equations that we'll be using in the future. Okay, so again, we're going to start with A equals dv dt, and that allows us to do a dt equals dv, and we're going to integrate between t naught and t of a dt equals the integral between v naught and v of dv. Okay, so now we can rearrange, and we are going to continue solving. We're going to get v naught minus v is equal to a. We can pull the a out because the a is a constant now. It's the integral between t naught and t dt. And this is equal to a times t minus t naught. That's wonderful. We've been able to solve that. So now we're going to go again, but with velocity, so v equals dx dt. So then we can solve again, so we get v dt is equal to dx. When we integrate between x naught and x, dx is equal to the integral between t naught and t dv, or v dt. So thus again we can solve, and this gives us a nice function. So we get x minus x naught is equal to the integral between t naught and t of v naught plus a of t minus t naught. Again, we're plugging in from an equation that we have up here once we solve for v. And then this is going to be with respect to t. And again, we can simplify. We can utilize the linearity again to sum. So we get the integral between t naught and t of v naught dt plus the integral between t naught and t of a dt, of at dt, and finally minus the integral between t naught and t of a t naught dt. Okay, and this whole guy is equal to v naught times t minus t naught plus 1/2 of a t minus t naught raised to the second power. So thus, we can find an equation for x, and this will be a big definition again. So we have definition. We have v, so we have x equals x naught plus v naught t minus t naught plus 1/2 a t minus t naught squared. And then v equals v naught, v equals v naught plus a times t minus t naught. Okay, so those are the equations of motion, and typically this t naught is going to be 0. So you can kind of see how you get that. And again, this is something that you can easily derive by doing indefinite integrals as well. Okay, so there we have it. That is one-dimensional kinematics, the important quantities, the preliminaries, as well as the integration of the equations of motion. Thanks for watching.